So here's a quick review of what we know up to now. If a projectile is launched off a horizontal surface so that its velocity initially only points along the x-axis and the initial vertical velocity is equal to 0, then as long as we know what this initial speed is, we just call it v, and we know the height of the ledge, then we can find the time of flight, we can find the range, we can find the final vertical speed at impact, we can find the angle of impact. So you don't need to commit these to memory. I think the point here is with the equations I'm about to list, if you have the time, see if you can rederive them from basic principles. So the time is the square root of 2h over g. The range is the horizontal velocity multiplied by that time, which gives us v times the square root of 2h over g. The vertical speed is just the square root of 2gh, and the angle of impact is the inverse tangent of the square root of 2gh divided by v, where here v really, we could call it vx, but we're just implying v is the given initial velocity and it happens to be in the x direction. Okay, so that's our half parabolic trajectories. So if it's a full parabola, meaning launched across level ground, provided we know the initial velocity and the angle, so v and theta, we can determine also time of flight, range, and maximum height. So the time of flight is double either the time to rise or the time to fall. So we'll say it's 2 times the time to fall, which means it's 2 times the vertical velocity divided by acceleration due to gravity, which means in the end t is equal to 2 v sine theta over g. The range is equal to v squared sine 2 theta over g, and the height is equal to vy squared over 2g, so in turn the height is equal to v squared sine squared theta over 2g. Well, there's no guarantee that a projectile has to follow exactly half a parabola or full parabola. You could have a case where it's some other portion of a parabola. So here it looks like it's a little more than half a parabola, right? Not quite full parabolic. Looks like it reaches its greatest height here, so we get half a parabola plus a little extra, such that the final position is elevated up above the initial position. If you were to run and jump hard off a springboard and maybe the water's down below at this level, then you might go flying in, once again, not quite a full parabola, right? Reach your maximum height here, so you've got half a parabola plus a little extra, and in this case, the final position is somewhere below the initial position. So in cases like this, how would we go about solving the problem? So I'll illustrate that with a couple of example problems. Just last spring break, I think it was, I'd gone on a ski trip to Mammoth Mountain, and it snowed really hard the first couple days there. So the lifts toward the top of the mountain weren't operating, and those ski runs were closed. And all day long, skiing on the lower runs, we could hear detonations going off, and that was ski patrol intentionally causing some small avalanches so that the one big avalanche doesn't take place while folks are on the mountain. So this is typical. Consider a case where projectiles are shot with a speed of 160 meters per second at an angle of 50 degrees, and they end up landing on the mountain a distance of 1.9 kilometers away. So there's a photo of an example of this, but let's try to draw a diagram that represents the numerical values given in this problem. So maybe you got something sort of like level ground. It starts to go uphill and then approaches a steeper mountain peak. So down here is the artillery that's going to shoot the projectile, and it's flying out of the barrel with a speed of 160 meters per second. The angle from horizontal is 50 degrees. It follows more than half a parabola, ends up striking the hillside, and I think what's implied in this problem is that the horizontal distance to the point of impact is 1,900 meters, or 1.9 kilometer. So that's not the range, but we will call it delta x. Range, I guess, well, maybe you can call it range, but I think range implies the distance that would be traveled in a full projectile. I guess it would be fair to call it range in this case too, if you'd like. Okay, then we have a value of delta y. So let's see, all I know is best advice is to keep the motion along the x-axis and y-axis separate from one another. So let's do this. The first question is probably a good guideline here. Anytime you have a velocity vector that points at an angle, you can reproduce that vector aside from the diagram that it belongs in. Okay, so there's our original velocity vector. Here it is, written by itself. And then we can show in red the horizontal component to that velocity. And in blue, we can show the vertical component. Now, note, we can slide this over here, and it's still the same vector, isn't it? So in fact, let's do that. Let's slide this over to this point. It's still just as long and pointing in the same direction, so it's still the same vector. Put that arrowhead back on it. Great. So we've got our Vy. I guess that's V initial y. And this one I'll call Vx. And I don't really have to call that one initial because that's redundant. There's no difference between the initial and final speed along the horizontal axis. Okay, so we've got the total velocity v, which is 160 meters per second at some angle theta. And as you know, Vy is just v times sine theta, and Vx is v times cosine theta. So if we crunch the numbers on this one, 160 times the sine of 50 degrees, or horizontal speed 160 times the cosine of 50 degrees. So you can grab your calculator, see what you get. So this comes out to an initial speed, a constant horizontal speed of 102.8 meters per second. And vertically, if we do 160 times the sine of 50, we get about 122.6 meters per second. Okay, so the acceleration is 0 along the x-axis. And this just means we can apply the dirt equation. This is just distance equals rate times time. Oh, so from this we could figure out how much time it takes until it impacts the mountain. When we rearrange the equation, time is horizontal distance divided by horizontal speed, and it lands a horizontal distance of 1,900 meters away, and it did so with a horizontal speed of 102.8 meters per second. So the time that our projectile spends in flight is equal to let me try that again. So Josh. Ah, 18.5 seconds in the air. Make a note, I think it's actually 18.47 if I want to keep a little more sig figs. Okay, so we've got the initial velocity. Now, the time, that's the one thing that links the horizontal motion and the vertical motion, is the amount of time that the object spends in the air. So there it is, we've got our time of 18.47 seconds, an initial velocity of 122.6 meters per second directed in the vertical direction. Let's put a frame of reference in here. We'll say there's 0, up is positive, down is negative. So this is a positive velocity to start with. Our acceleration is g, which we have to call negative 9.8 meters per second squared. So we're on our way to answering part B, and I already skipped over part A. We kind of had it. To put it in unit vector notation, we say v, and give that symbol here. Now we're talking about v as a vector. We have two choices. We can say it's 160 meters per second at an angle of 50 degrees, or we can say it's 102.8 I hat plus 122.6 j hat. That's our Vx, and that's our V naught y. Okay, so we already did answer A. Part B, at what altitude does it strike the hillside? So that's what we're trying to figure out. How far does it displace vertically in that amount of time? So nothing was asked about what's the vertical velocity. So, what's the component of the speed when it strikes the hillside? Now, that wasn't asked, that wasn't given, we'll leave it out. So the equation that relates these four variables is delta y equals v naught y times t plus 1/2 at squared. If I hadn't already found the time of flight, could I still solve this problem in one step? Let's see about this. This would give us delta y equals, v naught y is the same thing as v sine theta. Now that, in turn, that whole amount we already found is 122.6, but had we not found that, and we just knew that the v was 160 and the theta was 50 degrees, then I'd have to say delta y is v sine theta, okay, that's v naught in the y direction, times t plus 1/2 g t squared. Let me number the steps that I'm doing here. Delta y equals v sine theta, and then instead of t, I'm going to write in an algebraic expression. Not so much the numbers, but just this idea. If I divide x by the x velocity, so times x over vx, x over vx. Okay, vx is v cosine theta. And then plus 1/2 g, and then here's t again, but squared. So x over v cosine theta, quantity squared. Let's do step 3. I notice here I have a v canceling with v, and then you're left with sine over cosine, but that's the same as tangent. So you get delta y equals delta x tangent theta plus, and then let's just square everything individually, right? The x is squared, the v is squared, the cosine theta is squared, and then we'll just put it all into one fraction, so g also belongs in the numerator. So this would be plus g x squared over, don't forget this 2, over 2v squared cosine squared theta. So if you want, we could answer this question of how high along the hillside all in one step. Let's see, this would give us delta y equals 1,900 times the tangent of 50 degrees plus negative 9.8 times 1,900 quantity squared all divided by 2 times 160 squared times the cosine of 50 degrees, all that squared. Okay, let's see what we get. So this term gives us 2,264.3, okay? And this term gives us negative 1,672.3. And so we get an overall answer, delta y equals about 592 meters up the hillside. Let's just see if that's the same thing we would have got if we did this step by step. So here we already know that t is 18.47 seconds, and we already knew that Vy was 122.6 meters per second. So if we try this as a more direct approach, we can double check our work. So we would get delta y equals 122.6 times 18.47 plus 1/2 of negative 9.8 multiplied by 18.47 squared. Okay, so yeah, this gives me the same 2,264, well this time 0.4, but that's because the 18.47 is somewhat rounded off. And let's see. Yep, this gives me the same value, negative 1,600, well, this time 1,671.6, a little bit different, but this is just because I'm rounding off intermediate values. So when you take this two-step approach of finding the time as step 1 and then plugging that into this equation as step 2, that intermediate answer has to be rounded off, whereas this approach was all done in one step, and so there are no rounding issues along the way. So the answer very nearly agrees. Certainly to 3 sig figs, we're going to get the same answer, 592 either way. So we've got the velocity in unit vector notation, the altitude where it strikes the hillside, and how high is that compared to the maximum height of this projectile? You can see I have a second problem to work on here. Let me get that out of the way. So the maximum height, well, there's just a formula for that, okay? Maximum height is equal to v squared sine squared theta over 2g. So this is 160 squared times the sine of 50 degrees, all squared, divided by 19.6. And that comes out to 766 meters. So 592 compared to 766, not too much below. So it had very nearly hit the mountain at its maximum height. It just carried on a little bit farther. 766, 592. Hey, let's double check that. We could also just take the initial vertical speed, square it, and divide it by 2g. So 122.6 squared over 19.6. Yep, that gives me the same answer, 766 meters. Okay, so moving on to the next problem. You drop your friend off at her apartment building, and she has a balcony that leads to her front door. And before you drive away, she realizes that she left her keys in your car. So fortunately, she yells down to you, and you throw the keys up. So her balcony is 25 meters above the ground. When you throw the keys up toward her, they spend 3.9 seconds in the air, and they hit her hand with a speed of 13.5 meters per second. So we've got to figure out these two questions. How far from the base of the building were you standing, and what was the angle of your toss? So this one you've probably got to read a couple times and really think about what does the picture for this one look like. So spend more time setting up the problem than solving the problem. Visualize it, label quantities, and if you have the luxury of working with a classmate, ask and see if they've taken a similar approach to you. So I think it would look something like this. Well, there's the ground, and here's the apartment building. Maybe there's a staircase, and then her balcony's here. She sort of leans over the edge of the balcony, puts her hands out. You're down here, and you toss the keys so that they travel something like this and land in her hand. Okay, so if that's how you're picturing it, you've got it right. So our questions are, how far away from the base of the building were you standing? So delta x is a question, and the way you toss the keys, the initial velocity forms some angle from the horizon. What was the value of that angle? All right, so what's given here? Well, we know the total time of flight is 3.9 seconds, and we know that the vertical displacement was 25 meters. And we're just going to assume that, like, we're going to ignore the height of the body as part. We're just going to say, like, what we really imply by this 25 meters is that's how high above the release point from your hand the keys were caught, okay? Don't want to make it more difficult than it needs to be. So, we've got one more piece of information. The total speed when the keys hit her hand is a vector that points down and to the right. So it has a vertical component, and it has a horizontal component. Okay, those components are not given, but we are given that total speed is 13.5 meters per second. As always, we're going to treat horizontal motion and vertical motion as separate from one another. I think we need to zoom in on this vector diagram a little bit, okay? So let's see. We've got a displacement, and we'll put the origin here. We'll say, how about this time I say up is negative and down is positive. So delta y would be equal to negative 25 meters. The key's displaced upward, and upward is negative, all right? Acceleration is positive 9.8 meters per second squared. The initial velocity along the y-axis is not known, but the final velocity along the y-axis, well, that's not known either, is it? Okay. But we do have time of flight. That's 3.9 seconds. Oh, I see. So how about this? We can solve for the vertical component of the velocity. Anytime you have three quantities in a list of kinematics variables, you can always solve for a fourth given the correct equation. So we want the equation for the final velocity. If we've got, let's see, let's do this. Let's find the initial velocity and forget the final velocity. So delta y equals v initial in the y direction times time plus 1/2 gt squared. And then we're going to solve for this initial velocity. So let's do a little rearranging here. V initial y times t is equal to delta y minus 1/2 gt squared. So v initial y is equal to delta y over t minus 1/2 gt. So v initial y is equal to negative 25 over 3.9 minus 1/2 of positive 9.8 times 3.9. Oh, of course, this is 3.9 seconds. This is meters per second squared. So seconds, so we've got meters per second. Let's see, this is 25 meters divided by 3.9 seconds. Oh yeah, so our units are going to be meters per second. We should always check this in our work. I got a little hasty there. Okay, 25 divide 3.9. So this part is negative 6.41. Okay. And this is negative 19.11, all right. So we get negative 25.52 meters per second. And all the negative means is in the negative direction, which for us is up, and we know that the initial vertical velocity is indeed upwards. That's 25.52 meters per second. Okay. Now the horizontal velocity has to maintain a constant value. So let's see. Our delta x is unknown. Our time is 3.9 seconds, and our horizontal velocity is constant. Okay, so if we have the initial vertical velocity, now we figured that out. This is no longer a mystery. This is negative 25.52 meters per second. So now that we have that, we could solve for the final velocity. So let's stick to the study still of the vertical motion. Say final velocity equals initial velocity plus acceleration times time. So see, I'm always just going back to my basic kinematics equations for constant acceleration. Now we might end up deriving, for example, a new equation based off of that one, but it's always going to start from basics. So here's another basic kinematics equation. So let's call this step number 1. Step number 2, let's say, since we're just dealing with vertical motion, put the subscripts in here, change the A to a G. So the final vertical velocity is equal to 25.52 meters per second, negative 25.52 meters per second, plus 9.8 meters per second squared times 3.9 seconds. Okay. All right, so we get a final answer. Vy equals positive 12.7 meters per second. So that's going to help us label this vector diagram if we zoom in. So the problem is saying is your friend's holding out her hand, and here come the keys, and they strike her hand with some overall velocity at an angle of 13.5 meters per second. The vertical component to that final velocity is 12.7 meters per second. And the horizontal velocity, we don't know. Okay, but we form a parallelogram out of these velocity components, and we see we're really just looking at a right triangle. A right triangle in which we know two of the sides. We know the hypotenuse is 13.5, and one of these sides has a value of 12.7. So to figure out the missing side, which would represent Vx, we just use the Pythagorean theorem. And so Vx is equal to the square root of 13.5 squared minus 12.7 squared. And we get a value for Vx of about 4.58 meters per second. Okay, so we can take that information and put it back into our list. This is 4.58 meters per second. So now we've really figured out everything, right? We've got a total list of all of the quantities for the vertical components to the motion, a displacement of 25 meters upward, an acceleration of 9.8 meters per second downward, an initial speed vertically of 25.52 meters per second upward, and a final vertical speed of 12.7 meters per second downward and a time of 3.9 seconds. Horizontally, of course, acceleration is 0. That means the final velocity and the initial velocity both have a value of 4.58, so we just use the dirt equation. Distance equals rate times time. So the distance away that you must have been standing when you threw the keys is equal to 4.58 meters per second times 3.9 seconds. So that's a distance of about 17.9 meters away. Now we need to find the angle. Okay, well, let's zoom in on this vector diagram. So here you are standing on the ground, and you throw the keys upward at an angle. The horizontal component of that velocity is 4.58 meters per second. The vertical component to that velocity is 22 point, did I forget this already? 22.52, 22 or 25? Sorry, 25.52. And so we need to find this angle. Well, the tangent of the angle has to be equal to opposite over adjacent. So the angle we're looking for is the inverse tangent of 25.52 divided by 4.58. And we get an answer of very nearly 80 degrees. So there you have it. Okay, thanks for watching.